Okay, so let's continue. Alright, so we have these two new equations here. The first one is x final, or position final, will equal our position initial plus our initial velocity multiplied by time plus 1/2 times by our average acceleration times by t squared. Okay. Now here our velocity final squared will equal velocity initial squared plus 2 times by acceleration times by delta x. And just a reminder, delta x means x final minus x initial. Okay, so with that in mind, what is constant and what changes when something falls? Okay, so let's look at this. Let's start with position. When something falls, does the position stay the same or does it change? Well, the position changes, right? What about the velocity? At that moment that you drop the object, your velocity is 0, and then you have this much larger negative velocity, so you increase in velocity, whether it's in the positive or negative direction, right? So that changes. Now, what about time? Time for sure passes, so that'll change. But the one item that does not change is gravity. Okay, so if I just have an object that's in free fall, okay, well, there's the only force that's acting on it is gravity, then we call that acceleration due to gravity. Okay, and acceleration due to gravity is negative 9.8 meters per second squared. Okay. You could use 9.81 meters per second squared. Okay. So, whenever you're dealing with a situation like this, and you can assume that the only acceleration is gravity, I put the negative sign because I'm saying going down is my negative direction. Okay, so that's why I have this negative sign here. So, a hiker drops a rock that hits the water below 4.78 seconds later. How far down is the water? Assume acceleration is due to gravity. Okay, so let's just, like we should always be doing for these problems, let's draw a picture. Okay, we have a hiker. He has a rock. He's going to drop that rock. It's going to hit the river below. Let's establish an origin. I think I'm going to have my origin be right, where the rock is going to hit, okay, in the river. And then from here, draw a picture, establish our origin. We're going to list our knowns and our unknowns. Okay. So x final, and actually maybe in this situation we can do both, but maybe in this situation I'll say where we're starting is actually our origin. Yeah, okay, I'm going to call that the origin. So in this situation, when we hit the bottom of our river here, x final, that distance, that's what we're solving for. Yeah, how far down is the water? Okay, x initial would be 0, right? Because they're starting there, so 0.00 meters. Velocity initial, well, my initial velocity, the moment that I drop that rock, that very moment, my velocity is 0. My initial velocity is 0 meters per second. Velocity final is how fast the rock hits the water, and I don't have that information. Acceleration is due to gravity, so that'll be a negative 9.8 meters per second squared. And then time, well, this occurred in 4.78 seconds. All right, so we want to know x final, so let's use that equation from above, where x final equals x initial plus velocity initial times by t plus 1/2 acceleration t squared. Okay, so I've drawn my picture, I've established my origin, I've listed my knowns and my unknowns. Now I've picked the equation that I'm working with. So let's say we said x initial is 0. I said velocity initial is also 0. Anything times by 0 is 0, so this whole component's going to drop out. So x final is equal to 1/2 acceleration times squared. So x final is going to equal 1/2 times by my negative 9.81 meters per second squared times by my time component, 4.78 seconds, and that's going to be squared. Okay, so let's, right here, I want to do a unit analysis. Let's see if we do actually end with meters here. Okay, so we have 1/2, which is unitless, acceleration, which is meters per second squared, and we're multiplying that by time, which is seconds, but it's squared, so the unit is squared as well, and so we do actually end with units of meters. Okay, nice. Now let's plug it in our calculators. So we have x final okay, so I have my 1/2, just throwing that negative sign there. I have my 1/2 times my negative 9.8 times my 4.78 seconds squared, and my final answer is negative 112. 3 sig figs, 3 sig figs, that's just part of the equation, so that doesn't have sig figs that come into play. It's an exact number. And so our final answer here would be it's negative 112 meters from the origin. It is negative 112 meters below where I said my origin was, which was this initial position where we started. All right, let's continue with these practice problems. Okay, let me check on my time here. All right, so a skateboarder is moving at a constant velocity of 1.75 meters per second when he starts up an incline that causes him to slow down with a constant acceleration of negative 0.20 meters per second squared. How much time passes from when he begins to slow down until he begins to move back down the incline? Oh, interesting question. Okay, let's draw a picture. Skateboarder moving at constant velocity when he starts up an incline. Okay, so he was moving at a constant velocity, but now he's starting to go up this incline here. Okay, so this like moment that he starts up the incline. Okay, so there's my skateboarder. Okay, so there's my picture. Let's establish an origin. Let's say this moment that we're talking about here where he starts up the incline, that's going to be my 0, 0. To the right will be positive, to the left will be negative. Okay, so I've drawn my picture, I've established my origins. Now let's list our knowns and let's determine our unknown. So a skateboarder is moving a constant velocity of 1.75 meters per second when he starts up an incline. Okay, so velocity initial, 1.75 meters per second. And this causes him to slow with a constant acceleration. Okay, so final. Here's like my typical list of items that I'm typically looking for. Velocity, position, acceleration, time. Okay, so a constant acceleration of negative 0.20 meters per second. So that's our acceleration, negative 0.20 meters per second squared. How much time passes? Okay, that's what I'm solving for. How much time passes when he begins to slow down until he begins to move back down the incline? So we want to know, how much time does it take for him to get to a point where he's speeding and then goes slower, 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 and then he stops, and then that moment right before he starts to come back down, right? And so in this moment here, where he's at the top and he's about to come back down, a couple of things. First, that very moment when he comes to a stop, that would be 0 meters per second as far as velocity goes. Now, our x initial, we said our origin is right there, and so our x initial is 0 meters per second. We don't know how far up the incline he went, and we're solving for time. Okay. All right, we want to know the time component here. And we want to use an equation that doesn't have, let me pull out our list of equations here. We want to know our time component, and we want an equation that doesn't have x final because we don't know that information. So this has x final, so does that. This one does not. And then that's just a rearrangement of this one. Okay, so we can use either of those. That one has x final, that one has x final. Okay. And so we're wanting to solve for the time component here. So genuinely we could use either of these because they're just rearrangements of one another. So I have acceleration is equal to delta v over delta t. Okay, and a reminder, delta v is velocity final minus velocity initial divided by delta t, which is t final minus t initial. Now, t initial was just at 0, and then this occurred over some span of time, so that's just 0. So we could just call t final t. So we could say acceleration is velocity final minus velocity initial multiplied by, divided by time, and we want to get time by itself. So let's now multiply time to both sides of the equation because we don't want it in the denominator. What we're looking for, we want to move it to the numerator. And so that kind of took us to our equation before, where we had acceleration multiplied by time is equal to velocity final minus velocity initial. And then we want to solve for time, so we'll divide both sides by acceleration. And so time is equal to velocity final minus velocity initial divided by acceleration. Velocity final is 0. So we have negative 1.75 meters per second divided by acceleration, which is negative 0.20 meters per second squared. We got 2 sig figs and 3 sig figs, so our final answer will have 2 sig figs. So we get 8.8 seconds because of those 2 sig figs. Now let's make sure that we do in fact end with units of seconds. We took meters per second, we divided it by meters per second squared. When we divide by a fraction, that's the same as multiplying by the reciprocal. So meters cancel, one of the seconds cancels there, and we do in fact end with units of just seconds.